Thank you very much. Many thanks for having me here. Actually, everybody says thanks the organizers for having me here, but there are obviously invitees and there are highly improbable invitees, and I am happy to be among the latter. So I really thank the organizers for having me here. Okay, so I am a theoretical computer scientist. I teach here at Berkeley, and as you'll see, I could not help but being fascinated by some of the same things that you are fascinated. So I'm here to tell you about it. And I'm going to tell you about work with two friends, Santosh Vempala and Wolfgang Maas. There is, in the way I see it, I'm going to tell you about some great disconnects between brain and computation, which are the two subjects of this workshop. Two things I have loved in my life is babies and computers. Okay, so and babies can do some amazing things, and computers can do some amazing things, but there seems to be no intersection between what babies can do. And then another disconnect is the incredible things that we learn every day about brain anatomy and activity, and how slow we are marching towards the understanding of the emergence of the mind, of cognition, language, and so forth. I believe this is an incredibly fascinating problem, and I am very interested in it. I have been thinking about it for only 2 years, unfortunately. I don't know how I was so late in coming. But given my biases, I want to believe, I'm pretty sure, that the answer, once found, is going to be at least partly computational. So I believe that it will be fine, it will be nice, it will be good, useful, if people like me, more people like me think about this problem. But frankly, right now there are very few handles. Okay, you know, the question is, how does one think computationally about the brain? I know that this workshop is about thinking neurally about computation, so I'm pointing to that a different direction. But that's where I'm coming from. So you know, I'm eager to find a handle in this direction. And some old-timers like me remember this famous dilemma. Okay, you know, is intelligence symbolic or sub-symbolic connections? And that's, of course, a pseudo-dilemma. You know, we now know it's nice to put 3 Greek roots together, you know, but the real question is where is identify the boundary. We know that the answer is both, and we want to find where the boundary lies. And this is where I start. And I want to draw attention to an ancient concept, cell assemblies. You can find this picture in Donald Hebb's book, where he says that cell assemblies, he calls a network of neurons activated repeatedly during a mental process. Okay, so this conception has taken roots in the imagination of a lot of students of the brain. For example, Kenneth Harris came up with cell assemblies as an alternative explanation for irregular yet structured spiking. In fact, he came up with this, a much better picture of what cell assemblies are about. And a few years back, Busaki said that identified a widely discussed hypothesis that cell assemblies underlie numerous operations in the brain, and for example, memories, mental processes, and so on. So, what are the conjecture roles of assemblies? one thing is to maintain through integration, robustness, and stability. A little more imaginatively, people have opined that this is how concrete world ideas are represented. For example, there might be an assembly represented this way, so that every time it is activated, it is coterminal with thinking about the idea of perhaps an almond. Okay, so I propose this as a boundary where computation as we know it can start. But the question is, how do you compute it with the brain? It could be that assemblies are the answer, but then the question becomes, how does one compute the assemblies? And one answer that I'm going to propose, and actually it has been proposed in the literature a few times, for example, by my fellow computer theoretician, Les Valiant, back 20 years back, when he wrote this very, very daring path-breaking book, Circuits of the Mind, that there could be gates of assemblies, very much like the gates that we see in ICs. For example, it could be the join of two assemblies. Imagine you have an assembly A and an assembly B, and it would be nice to have a third assembly, to create a third assembly, to create a gate, which is the join of A and B. And join means that if both of these are activated, then the join will be activated. A second operation, join will be a big part of what I'm going to tell you, but the second operation is the link between two assemblies. If you have one assembly and then another H, and you want, for example, you heard that almond is a healthy food, and you want to, every time you think of almond, to bring this thought back to mind, maybe there is a way to link this assembly, so that every time A is activated, then H will also be activated. Notice that this is not akin to something that is well known in cognitive science as variable binding. And as Legenstein and Maas pointed out to me recently, there is a subtle difference, and that's that this second assembly H may not be an assembly at all, but could be an important, a huge brain area, okay? In the case of, for example, variable binding of read to verb, okay? And a few years back, a couple of years back, with Santosh Vempala, we proposed a variant of join, which incorporates the concept of prediction that Bruno brought up in his talk. In particular, of course, every time A and B fire at the same time, join of A, B is going to fire. But now, if only A is activated, join is not quite activated, but it is mobilized, and it predicts B. And if B is itself a join, then it will also be mobilized and predict downstream. So these are very primitive ideas about how you could have gates created of these hypothetical things called assemblies. There are challenges, all right? For example, is there evidence that such gates are around? And the second one is I showed you as a game that you have two assemblies, and then you create their join. I mean, can this be done in any realistic way? Of course, important number three, what can they be used for? What can such gates? How can you do actual computation with these gates? Okay. So there is evidence of that the join of assemblies may be taking place. For example, in rodents, it has been measured a few times, it has been noticed a few times that, and not actually a few years back, that the composite memories are created. For example, stimulus or appetitive, or of the triple smell, ambient, color, reward. And in primates, it has been exhibited that memories of two different views of an object can be combined into a single memory. And recently in humans, in a paper by Eisen et al., they did the following experiment. We find this a very striking result. After you combine a person with a landscape, for example, your brother with in front of the Eiffel Tower, then after this combined image is shown, then a neuron previously responding only to your brother now also responds to the Eiffel Tower. Okay, so now let's go to the second challenge that I identified. How are these gates formed? And for example, join and p-join and so on. And Valiant, what Valiant had shown and what Vempala and I have shown for the more complicated construct of predictive join, that they can be, in principle, put together, and not by assuming any connectivity, by essentially recruiting new elements and taking advantage of the randomness in the network, okay? And not assuming even that the network is uniformly random, but taking advantage of any randomness available in the network. And in current work with Wolfgang, we are revisiting the same problem, trying to see if these constructions can be carried out in a way that is, in a more meticulous way, consistent with what we know about plasticity, inhibition, and so on. And of course, in the light of the results of Eisen et al. that I mentioned before. So now let me turn to the other challenge of what are they good for, and I'm going to show you an observation by our group, by Vempala and I, that they can solve a very simple task, but in an interesting way. The task of unsupervised memorization of a particular pattern, like this binary pattern. And basically, what I mean by unsupervised memorization, I mean that after we present this pattern in some presumably sensory cells for a few steps, in some sense, spontaneously, predictive joins are formed in such a way that in the end, one particular assembly is put together which memorizes this particular pattern. And the kind of algorithms I'm going to show you are not unlike the ones that Jeff Hawkins has shown me in the past, and Pentti Kanerva is going to tell you tomorrow. But the point is that we take sort of a slightly different point of view and focus on the gates that produce them. Okay, so let me go through. So this is the spontaneous algorithm, which basically says you just show it and you let the spontaneous creation of these new gates take over. Okay, in other words, there is absolutely no logic or rhythm or cleverness in this algorithm, so if a pattern is presented, and now I'm running through the simulation slowly, but the point is that predictive joins are being formed completely spontaneously, and in the end, this memory is formed. If the same pattern is formed, then prediction will be so rapid that no new hardware will have the chance to be created, and essentially the final assembly that symbolizes the fact that captures the fact that this has been recognized will light up. And if a different pattern is presented, in other words, here a few bits have been changed, then the hardware we have will be reused, but some new hardware will have to be built in order to capture the differences. Okay, and the theorem says that this works, okay, that it works without building too tall trees. In the final minutes, I'm going to switch to another place where I believe that gates are crying to be used, and that's language. Language, as you know, is something that was created by us yesterday. Okay, so and in some sense, it's an evolutionary adaptation that happened very, very recently, and it's very reasonable to assume that it evolved in a way that exploits the brain strengths. In particular, I'm pretty sure that the language you speak and the languages you speak everywhere in the world, they're optimized so that babies can learn them well, easily. Let me remind you a 60-year-old theory that is still evolving, and this is sort of its minimalistic version that is still in force. So, what is knowledge of language? Chomsky thinks that when we know a language, that means that we have grammar. And that some grammatical knowledge, and we'll see that this can be very minimalistic, predates experience, is innate. What do you need? What kind of brain functions do you need in order to have language? It turns out you need extremely little. You need binding to understand that some things are nouns and some things are verbs, for example, and you need merge, okay, to understand that a sentence has an actor and an action. For example, let's take this toy grammar. It has many rules, but let me point out the bold one. The bold one is the basic rule of all language. Okay, it says that what is worth telling has an actor and an action. Okay, that there has a noun phrase and a verb phrase. All right, and this is sort of the grammar in some sense is dead in linguistics, almost completely, except for this rule. Okay, this is the only rule that holds. All right. So, and how do you learn grammar? First of all, you learn very basic vocabulary, you learn one by one that some nouns belong to this innate category, probably some area in the brain that is noun phrase. Then verbs, you learn about verbs very much the same way, another innate category. And then you learn sentences. What is a sentence? A sentence essentially is nothing else but an actor and an action. And in some sense, this is what linguists call merge. To my mind, it is very much like P-join. Okay? And of course, sentence is also innate. Then you have generating and parsing sentence. To my mind, generate is much more fundamental than parsing. Parsing, I think, is an afterthought, is a sort of a reverse engineering generation. But you notice that several places there is a merge, but there is, of course, the merge, the main dichotomy in language, that there is actor and action. Okay, so that is, and this way you can parse and generate language sentences, and here is another sentence which involves recursion. And the same way it can be parsed. The point is that it's learnable. Okay, we have a theorem that says that all rightly recursive grammars, essentially avoiding what linguists call center embedding, and which always gives trouble to language learners, can be learned efficiently from a well-chosen sequence of few examples. Now I'm coming to the fascinating part. I think that, so in the past 10 years I've been studying evolution, and I believe that the brain should be is the least studied but most fascinating object subject in connection to evolution. So I'll tell you a few ideas that I agree with, and I had anticipated, but came out in a very interesting book by Berwick and Chomsky, Why Only Us? It is tempting to believe that language is not so recent as we think, that language had been ours for about 1 million years. But for the longest time, we sort of, it had been just inner language. Inner language because we could only growl, okay? We had no vocalization. And this, however, inner language was still extremely helpful, extremely important for our ascent. For example, it gave us planning, reasoning, logic, math, stories, okay? Inner stories. And then maybe 100,000 years ago or less, if you think about it, that's 3,000 generations, okay? That's an incredibly small amount of time. Somebody in a cave somewhere started vocalizing. Okay, sort of, and then it spread, and language became vocal, language became social and learnable, language became mutable, and so we have English and Farsi. Okay, so evolvable. And the rest is prehistory, okay? So that's this could be the most fascinating story of all. One last coming back to neuroscience. One last point. Could it be that the merge is innate? Okay. So this is a slide from a paper by Frederici. Where they have discovered, they have found that there is, in the left hemisphere, unfortunately it also exists in the right hemisphere, with some modifications. But certainly in the left hemisphere, there are 4 pathways that are, first of all, they seem to be specific to humans. And second, they are apparently myelinated just before the 2nd year of life. So as soon as syntax arrives, okay. So and one makes you wonder. I mean, what does this have to do with the emergence of syntax and the sort of the growth of the merge? All right. So just to review. Well, I believe that cell assemblies are a very interesting way to start thinking for computer scientists like me, to start thinking about computation in the brain. I believe they are both plausible and they accomplish things. Okay, and I told you I gave you a few examples. What I want to emphasize is that the novelty from other proposed circuits is that they don't require special connectivity because they recruit and get new material from the randomness and chaos of the brain. And I told you about unsupervised memory pattern memorization, and I also told you about language and its evolution and what merge could have to do with it. So that's it, and thank you very much.
So,
Sure.
So this might be a question to kind of prime the discussion section a little bit, but I really enjoy your cell assembly model from a theoretical computing point of view. But from the computational neuroscience point of view, I'll tell you the disconnect that I've often seen in connecting that approach with, and things like connectionist models and symbolic models, and what the neuroscience community builds is time. Mm-hmm. Right? Neuroscience models, or neuroscience, is very dynamical in nature. And these are, this is kind of very algorithmic, explicit time, kind of stepping through approach. And so, I realize that there are ways of combining those. I'd just like to hear how you would approach that. So how, take the dynamical systems view of the brain and link it with your cell symbol model.
So I totally appreciate that. I had a little sentence, which, so I'm sorry if I repeat myself, but what assemblies do, first of all, they let me focus and understand what I'm doing better. But what they do, you can say that they are through integration. Integration both of expression but also of impact. They stabilize. Okay, they become more robust. Okay, of course, attractors are another great way of doing this. Okay, but cell assemblies are another. Okay, so they happen to be one that I can understand and work with. Hi.
Sorry. It would be a crime not to ask you to comment in some way on the computational complexity of neural processing, although I can't frame a good question for it.
I'm sorry. So what computational complexity of
neural processing? I don't have a good question to frame that, but it just seemed criminal not to ask you some question on that.
So it would be criminal not to have a good answer for that. So computational complexity deals with artificial environments and input. Deals with problems that are presented in artificial environments. Okay, because for all our algorithms, okay, most of their inputs are generated by other algorithms. All right, so we have been optimized. Our brains have been optimized to survive and thrive on this planet. Okay, in a boring planet, our brains would do absolutely nothing. Okay, so but basically, I think that we are tailor suited to the fascinating environment around us. Does it help? And as a result, computational complexity, as we studied, for artificial systems, seems to me irrelevant because these are algorithms that have been completely tailor-made for their inputs. Okay. Okay.
For the discussion session, and then we'll have it just a very brief discussion, sort of couple minutes of comment from the speakers, and then we'll open up to the audience as well.
There's a gentleman who has been queuing for a question.
Go ahead, actually, if you'd like to.
So I really appreciate you thinking about language and so forth and so on. Now, I've been studying this for 30 or 40 years, and I find that you have it kind of backwards. So a dog does merge and binding operations all the time. It's called
Totally agree.
reinforcement learning. Okay. So to say that that's language is completely wrong. Okay. So what I see as language are structures, are things that are showing what the neocortex is actually doing to communicate to another neocortex. And what you're describing from Chomsky's work are some hints, but Chomsky is really not a computational guy. Okay. So he really doesn't understand computation and so forth and so on. So there are hints in the grammars and so forth and so on. I think that I think you have it backwards. So language, the way you're describing language, is actually, pick a number, 100 million years old. The language that we use
Dogs are younger than that, but anyway, yes.
is
okay,
actually
yeah.
another thing entirely. Okay.
Yeah.
And I think that the parts of it are not simple, like merge and bind operations, which have been with, mice. Okay. The problem is understanding what language really is in terms of how it reveals how the neocortex operates. It's just an opinion on mine. And I've been doing language
Thanks for your
a long
comment.
time.
I could not agree more with you, and that's in fact an important point in what I was trying to tell you, that language cannot be just explained by merge and binding, and the reason is that, as you said, these are cognitive operations that are quite basic. The point is,
I actually disagree with that one too. So my argument is that yes, Chomsky does capture a piece of the puzzle, okay, but there's much more interesting things in the puzzle than what Chomsky was able to capture with his way of thinking about stuff. So
okay, let me agree with you. There are much more interesting things about language that we understood from my talk. Okay, so okay.